Hello everyone. So this is our another technology seminar today by Mohammed MALEKAN from Iran. He hailed where he completed undergraduate studies in aerospace engineering at Tehran Polytechnic in 2009. He pursued further education at Tarbiyat Modares University in Iran, earning a master's degree in structural design in 2012. His academic journey then took him to Brazil, where he received his PhD in computational fracture mechanics from the Federal University of Minas Gerais in 2017. Following nearly 4 years as a postdoctoral researcher at the University of Sao Paulo in Brazil and Aarhus University in Denmark, he joined the University of Southern Denmark as an assistant professor in 2021, subsequently achieving the rank as an associate professor in 2023. His current research focuses on computational fracture mechanics, experimental solid mechanics, tribology, metal machining, and the analysis of both metallic and non-metallic components produced through additive manufacturing. So we will listen a seminar focusing on this topic. Thank you for coming here and giving the talk.
Thank you. Thank you for the nice introduction. Hello everyone. This is Mohammed. So I'm not going to further introduce myself. I think it was a complete introduction. And the topic that I'm going to present today is about our recent works in the last 2 years on the macromechanical behavior of additively manufactured metallic parts based on static, mostly static testing, and also dynamic testing, and also macrostructural evaluations. So the topics that I'm going to cover in this presentation are a little bit introduction to our research group, Smart Structures and Manufacturing at the University of Southern Denmark. The topic of additive manufacturing a little bit, dive into the topic for those of you who are not that much familiar with additive manufacturing. Static testing that we did for 2 different metallic alloys, and then numerical modeling as well that we ran to simulate a little bit of the process and to compare with the experimental analysis, and also dynamic testing. And then the last part of the presentation is just a conclusion of the whole talk. Smart Structures and Manufacturing Group was established in a few months after I joined Center for Industrial Mechanics at the beginning of 2022. So it's a young research group. We are 2 permanent faculty members, myself and also a colleague, Pei. There is also a visiting professor, Bijan, and we do have 3 PhD students, and all of those PhD students are being supervised by me. So Deborah is working on the fatigue analysis of titanium alloys produced by cold metal fusion, a different additive manufacturing process. Jansen is working on the fatigue crack growth of metallic parts. So different alloys, again, it's going to be stainless steel, aluminum, and we are going to evaluate the crack growth in those alloys when we change different process parameters, different sample sizes, and so on, because as you may know, additive manufacturing is a kind of a complex process, and there are a lot of process parameters, and each one of those process parameters, they affect the final part quality and also macromechanical behavior. And Khaled is our recent PhD student who is going to start from 1st of January, and he's going to mostly focus on numerical modeling of additive manufacturing process, especially focusing on temperature distribution, residual stress distribution, and also macrostructure formation, and mainly to combine that with our experimental observation and help us to optimize overall process. Because as we know that, for example, like evaluating residual stress and so on is not easy using live the process of additive manufacturing. And 2 former members, one of them is Dr. Rashid Ahmed Yildiz. So he was with us for 2 years and as a colleague, a researcher, and helped us a lot. And most of the content of this presentation was in a joint collaboration with Ahmed and a research assistant. So we are kind of in a growing process. Again, it's a young research group. And what we do in this research group mostly are fatigue and fracture, of course, of both metallic and non-metallic materials. Recently, in the last 2 years, we focused mostly on additive manufacturing, but we do also analyze components made by conventional manufacturing as well. And mainly, our aim currently is to compare them, the capacity with additive manufacturing, to say, okay, when it comes to industries and so on, because those are the end users when it comes to metal additive manufacturing. So if they want to replace a part by those produced by additive manufacturing, so functionality should be the same, life should be the same, and so on. So in that regard, we also investigate conventional like the materials, mainly to have some ideas, to have some kind of estimation of what our fabricated additive manufacturing parts should behave. And of course, additive manufacturing, computational methods, basically to reduce the kind of cost for sure, because of course we do have equipment to do experimentation, to produce parts, to do experimentation, static or dynamic, microstructure evaluation, but we know that it's time consuming, but also costly. So that's why we use computational methods to help us to analyze some of the field variables that we cannot capture, or it's a little bit kind of expensive to capture using experimentation. Multi-scale topology optimization of metal materials, and that's something that we can use additive manufacturing to build metal materials, so structures with a kind of either regular or random kind of shapes to produce, so it's not easy by using conventional manufacturing, but additive manufacturing gives us that opportunity to produce complex cellular or metal materials. Piezoelectric materials, variant tribology, metal machining, and also structural integrity. So you can just like scan this QR code to know, access our web page, like the LinkedIn and so on, for further information. And what we have in this group, there is a lab called Fatigue and Fracture of Materials associated to this research group, and there are different capacities in that lab. So we can do static testing, dynamic testing with a really good capacity for our purpose, 100 kilonewton capacity when it comes to dynamic testing. And there is a frequency range that we can go up to 100, 150 hertz, but of course not with the full load capacity. When we go to high frequency, so we should lower the load. And recently acquired tribometer, basically to do like the tribology related kind of activities, starting with the kind of wear and friction. So currently we do have this tribometer equipped with a pin-on disc system, and we can apply a load up to 200 Newton, which is good for most applications. And a dynamic mechanical analysis for smaller samples, but with a capacity that we can have a chamber over there, and we can change, for example, the temperature, either to go to like the kind of a cold, like a minus 50 or 100, something like this, or hot kind of environment, mainly especially for polymers in that case, to test them, static, cyclic, creep testing as well. And in near future, we also are going to have a kind of an environmental chamber for both these static and dynamic testing devices, that we can also test metallic components from minus 129 to plus 350 degrees. So to see what's going to happen, we know that temperature changes mechanical behavior, and we know that some of the components might be function in a different temperature than the room temperature. And also a digital image correlation system, DIC system, basically to capture some of the field variables such as the stress and strain live similar to what we can do using like an extensometer, but not only a strain, but also stresses that we can get, especially when we do some kind of fracture testing in our lab. Yeah, that's just was kind of an overview of what we do. So going back to the main topic of the presentation, additive manufacturing. Based on ISO or ASTM standard, so there are different classes of additive manufacturing when it comes to metallic materials. So metal additive manufacturing. There are 7 categories, and 4 of them are direct metal additive manufacturing, classified as direct metal additive manufacturing, such as powder-based fusion, direct energy deposition, binder jetting, and also material not material extrusion, no, sheet lamination over there. And by direct kind of metal additive manufacturing, it refers that the components that they build out of those technology are the final components. So that's direct metal additive manufacturing. And different forms of the processes, each one of those. So the feedstock is different. So some of them are powder-based, some of them, for example, sheet lamination or wire-based. So different kind of feedstock. And technology is more or less similar, but the outcome not exactly similar, in a way similar, and other ways are different. But the outcome also going to be different. For example, in some cases, we are going to have a surface roughness of order of millimeters. In some of others might have, for example, powder-based fusion might have the surface roughness of order of tens of micrometers, something like this. And macromechanical behavior as well will be different. And indirect approaches such as photopolymerization or material jetting and also material extrusion are 3 indirect metal additive manufacturing, which the parts that we produce using these technologies might be used in a later stage to produce final metallic parts. So that's indirect metal additive manufacturing. And what I'm focusing mostly in this presentation is the powder-based, which we have a device as well in our center. And metal additive manufacturing, just a general overview, is a process that we build the product or the part that we like layer by layer. So this, especially this, for example, here is just a powder-based. So you have the first layer, then the laser comes, melts based on the strategy that user defines, the scanning strategy, and then once it finishes, the next layer comes, and then the same process based on the geometry that provide. So the process is that we have our CAD model that we would like to have, and we have that CAD model, we transfer it to kind of having everything that, for example, this information, such as the number of layers, scanning strategies, together with the process parameters. There are a lot of process parameters, and I'm going to mention some of the important ones. And then we're going to have a file set, such as, for example, a STL file or 3MF file, something like this. And then we transfer it to our machine. So we produce, we cut it, and then if we need, for example, post-processing, such as, for example, surface finishing or heat treatment, for example, then we do, and then we're going to have our final part. So that's the overall process. And metal additive manufacturing is a kind of still growing. Of course, it's not nowadays at the end of 24, we cannot say new technology anymore, but it's growing. So, and there are different reports, so this is not the only one. There are different reports that there are some forecasts for metal additive manufacturing. And for example, this one, so forecast that by 32, so the market will be 18 billion US dollars. So it's a kind of a huge market. And mostly that market is going to go to new technologies and innovative materials. So new technologies that how we produce like the parts and components with, for example, lower porosity levels, for example, better mechanical properties, macrostructures as well, and new materials that we can, regarding the different type of materials. There are different technologies, but of course, it's not the case that we can produce any material that are available. similar to what we do in conventional manufacturing. So that's not the case. New materials that we can use, for example, in terms of powder size, morphology, and also property, and maybe combining different kind of chemical compositions to have a new material that we can use to produce those complex shapes, for example, right? And that's mostly the technology. And we try to go, not exactly because I'm not a material scientist, so that's for sure. I'm a mechanical engineer. Of course, by education, I'm an aerospace engineer, but later, so in the category of the water mechanical engineer. I'm not focusing on the technology itself. Technology itself, for me, is not a complete black box, because I'm also would like to evaluate the process itself, because that's also something that if we do some mechanical testing, without knowing the process and what is happening there, we cannot understand and we cannot control the process, because we as a user, we give the machine what kind of process parameters the machine should use. Should it be like the static process parameters fixed during the whole process, or a dynamic type of process parameter? Let's say if I want to produce this part, and then should I use, if this is 1,000 layers over here, so should I use the same process parameters? Or because of some geometry changes, I need to change the process parameters over some regions, mainly to control level of the porosities inside, surface roughness as well, right? And that's the case that we need to understand the process. And for us, that's the focus. The process itself, not the technology, and the combining with the mechanical testing and numerical simulation and so on. Yep. And laser powder bed fusion technology, so is one of the direct metal alloy manufacturing, as I said, and in a kind of a simple schematic is like this. Exactly this is the schematic of kind of our machine as well. That we have a powder reservoir on one side, and then we have in the middle side, we have our build plate, and then we have excess power going to the other side. And so we have the laser, and this laser follows our scanning strategy, speed that we say to the software, and other process parameters. And we gradually, once we have the first layer, so the next layers, this build plate goes down exactly with the same size as the layer thickness that we define. So that's the whole process. And we use a laser to selectively melt powders. And we have also non-melted powders in some cases that they can be served at a support for the manufacturing part. In some cases, not all of them. For example, if you have an angled one more than 45 degrees, then you need to have some supports, mainly to hold our part, the printed layers. And we have a cooling rate of 1,000 to 10 power 8, like the Kelvin per second. So that's the cooling rate in this process, depending on the size of the process parameters, like the power, and also depending on the machine. And it's a highly efficient in printing parts with complex geometries, right? Like the cellular structures, metal materials, those type of geometries, especially, and for those some other geometries that if you want to use conventional manufacturing, then maybe we need to have 10 or 50 different parts, and then we have to use welding or bolts and so on, and joints to have a single system. And then we can use this technology to produce. Of course, the build chamber is not that big. So it's not similar to the direct energy deposition or wire arc additive manufacturing that we can, for example, produce parts in the size of meters. Here, for example, in the case of our machine, so the build plate is 15 by 15 and 25 centimeters. So that's the build plate. Of course, it's not the biggest machine that you can have based on powder-based, like the kind of technology. It's a research one, but the overall kind of build plate for powder-based systems is in that order. It's not meters, it's centimeters, okay? And that's one of the limitations. And main applications are in medical and aerospace industries, where part customization is crucial. And one of the reasons is that we don't use it for larger structure is because also the production rate is low. So it's not similar to direct energy deposition. So here, for example, the speed that we can go is, for, I don't know, maybe maybe 2 meters per second, something like this. But in a direct energy deposition, it's higher. So we can have a larger part in a shorter time in that technology. Of course, it has each one of those technologies, they have their own pros and cons, right? Like the again, surface roughness in the wire arc additive manufacturing, direct energy deposition. You might need machining afterwards. We cannot use directly the part, but here, depending on the level of the surface roughness that we would like to have, maybe we can directly use that one. For example, in the case of the medical implant, in some of the majority part, maybe we can use directly the part for the purpose, not the whole one, because some places we need to be shiny, but other places maybe we can use even surface roughness, maybe even we are looking for surface roughness in case of medical implants, mainly to have a better kind of bounding. Of course, not directly, maybe we want to, if the material itself is not biocompatible, you need to do some post-processing to put a kind of a coating on top of it. But otherwise, we can use the same software, the same part without doing any post-processing. And as I said, there are many process parameters in any of those additive manufacturing technologies, especially in the laser powder-based fusion. We have also a lot of process parameters, but the most important ones are the laser power, laser scanning speed, and also spacing, spot size. So laser power, spot size refers to this beam diameter. So we have the scanning speed, and we have this hatch spacing or spacing that we are referring over there, and also the scanning strategies, layer thickness. So all these parameters affects the mechanical response of the produced part. So if you have, for example, smaller layer thicknesses, so we have a kind of we keep the same laser power, then we have a kind of a situation that we even remelt some of the sublayers, okay? Not only the current layer, but also the sublayer as well. And then that remelting helps to have bounding between the top layer and the previous layer. And that helps the kind of also the growth of the grains as well, not only in the single layer, but across the layers as well. And all those process parameters affect, for example, microstructures such as melt pool geometry, porosities, locations, grain size, surface roughness, not microstructure, but in that category. And also on melted powder, for example, residual stress as well. For example, if you change laser power or scanning speed, directly we saw that, and we're going to show that as well, that it heavily affected the level of the porosity of the produced part. And those microstructures affect the final the properties of the part. Do we have any anisotropy in our material, for example, depending on the printing orientation, if you printed in the same direction as the build direction, or if you printed in the angle direction, so it affects the anisotropy, tensile strength, ductility, hardness, and different mechanical properties. But the set of those process parameters, if we optimize those process parameters for example, one of them, if we want to have the best tensile strength, it doesn't necessarily mean that those set of process parameters are going to give us a best fatigue strength. So that's not the case that we saw in our mechanical testing. So after going to the introduction to the additive manufacturing, let's go to what we did based on this technology. So we did, first of all, with the static testing, 2 different alloys, and one of them was a stainless steel 316L. And we can see here the chemical composition and also physical properties of the metallic powder that we used. And the application of this alloy, you can see that, for example, petrol is mostly 40% goes in petrol, and then we have biomedical application as well. And we wanted to evaluate that one as well using our machine. As I said, when we use, even with the same technology, even with the same, let's say, powder-based, laser powder-based, like the based fusion, even with the same technology, if you go from one machine, from one manufacturer to another machine, but we keep the same technology, the produced part, the behavior is not going to be identical. Even with the same machine, the same process parameters, the same powder, if we produce one part now, and then we put another run, we produce another part, these two are not going to be identical, mechanical properties. And that's one of the limitations that industry is hesitating to adapt at the manufacturing into their like the daily production kind of line. That's one of them. Like the reproducibility, that if you produce one part and if you want to have 1,000 parts, the quality of those 1,000 parts should be similar. So that's exactly what they achieve using conventional manufacturing, right? And the other alloy that we used was Inconel 625. A different application, some applications similar. For example, in the case of medical, also we see here as well, mostly in aerospace because of the corrosion resistance. For example, like the turbines that they use Inconel nickel-based alloys in that application. So we alloy that one as well. And our machine has the metal printer that we have is not a part of our group, is a different group, but we have a collaboration and it's a part of the same center. And that machine is capable of printing aluminum as well, copper. So at the center we already did this printing of aluminum, copper as well, and potentially titanium. We didn't print any titanium yet, but that's also part of plan of our colleagues to do the titanium printing as well. But what we did in here, we only focus on these two alloys for now to evaluate their static and dynamic properties. So when it comes to stainless steel, again, coming back to different process parameters I was discussing in powder-based fusion, laser-based powder bed fusion, is that we focus only on scanning speed, layer thickness, build orientation, and laser power, only on those 4 parameters to see the effect of each one of those parameters on the mechanical property. So that was our aim. And if you combine all these parameters, we can see that we can also have a single parameter having all those except build orientation as a volumetric energy density. So we can, a single parameter that combines 3 that we see here, but also hatch spacing as well that we don't see here. And the hatch spacing for all of this were set equal to 50 micrometers. And this volumetric energy density, as we can see, is that if, for example, if we increase power, so melting will be a little bit harsher for the powders, and we are going to have a higher volumetric energy density as well. And then if we decrease, for example, velocity as well, we're going to have the kind of a higher volumetric energy density. And if we, for example, if we decrease like the speed over here, as what we see is that we have the laser spends more time over the same the kind of length span, right? And then that it transfers more energy to the powder, and that affects also mechanical property. We are going to have a kind of, for example, melt pool that we're going to see later as well, changes when we change those parameters. The size of the melt pool, width of the melt pool, and also depth of the melt pool changes with those parameters. And we use this machine, Exact Metal, XM200G printer to produce our parts. This is exactly our machine. And there is a small bead chamber over here that we can see. Also, there is a small window that we can look at what happens inside the chamber. And also, we can also see different process parameters that we are introducing to the part lively over here. But again, in this machine currently, we don't use dynamic process parameters. So everything we have is just a static process parameter. So the fixed process parameters at the beginning of the printing, and that's it. So the whole print is going to be based on that fixed process parameters. But there are machines, LPBF machines, that also do this dynamic change of the process parameters. So while you go layer by, not exactly layer after layer, but depending on the geometry of the part and so on, they change process parameters along the print. So that's also a possibility. It might be a possibility in our machine, but we haven't tried that yet. But we want to try that one as well to see what happens. And for in-canal, almost we did the same changes that as we did before in stainless steel. So changing scanning speed, layer thickness, build orientation, and power. Again, the hedge spacing was kept equal to 55 micrometers. In stainless steel, what we did, we also changed another parameter, laser beam diameter. So we changed that one as well. We had two different laser beam diameters. One of them was 50 micrometers, the other one was 100. And in the case of in-canal, we use 100 micrometer kind of laser beam diameter. So that's the difference between these two cases. And so this was our first work, and this was the second. As we can see that we add also another, like the kind of set of experimentation, we call it optimized. So as we saw from our previous mechanical testing and also initial mechanical testing over there, that, for example, among those scanning speed that we tested, and also layer thicknesses that we changed from 30 to 80, and build orientation as well, and also the power. So smallest scanning speed, smallest layer thickness, and vertical direction printing, so in the same direction as the build direction, and also the highest power gave us the best mechanical property, which means, if you can look at that, so the highest volumetric energy density as well. But it doesn't mean that this is actually the best or the optimized set of process parameters for this device, for this alloy. That's not the case. So don't get me wrong. That's not the case. Among the tested, this is the optimized set of process parameters. So if we decrease, if we like the kind of have the half of this power, okay, laser power, and also half of the scanning speed, still we're going to have the same volumetric energy density. So we expect, based on the literature, so we expect to have the same quality, but we didn't test that. We want to do that as well. So we want to go to lower speed as well. Of course, it's not like the kind of favorable to go to lower speed, because if you go to lower speed, it means that the production rate is low as well, right? If I go 1 meter per second, or if I go to 0.5 meter per second, so I know that the production rate is going to be lower. But we wanted to test, again, because LPBF is for special cases, okay? If you want to have an implant, for example, you're not going to produce, nowadays, especially nowadays, you're not going to produce 1,000 similar implants, right? Nowadays, for example, in the case of the medical application, we have patient-specific implants. So for each patient, we're going to have a dedicated implant based on CT scanning. So we're going to produce only one. So if I use even 0.2 meter per second, that's okay, because I'm going to produce only one, not thousands, okay? And that's why that's also a target of our research group, to do further analysis of those process parameters while having similar to this, the distribution of similar to this of volumetric energy density, but manipulating other process parameters together and compare with this, right? And that's our idea. And based on those set of process parameters, we can see here the static testing, a stress strain curve, a typical way of evaluating materials in a static condition. And as we can see, for example, when we have like the lower laser power, which means also lower like the kind of volumetric energy density, for example, if we go there, so the lowest one goes with the power of 100, so 30. And that's also the worst condition when it comes to static testing. And that also we expect to see. What we wanted to see, again, for our machine, because we wanted to evaluate. We didn't do any evaluation of the machine itself before, so we wanted to evaluate. And we know that we are not the first researchers doing this kind of stuff, okay? Using LPBF, print, for example, stainless steel that you see a lot, do a static testing as well, and compare and change process parameters. We know that, already knew that as well, but we wanted to evaluate and assess the effect of those process parameters when using this specific 3D printer, okay? And that was our aim. And we saw kind of something that we expected as well. And we changed laser power while keeping other process parameters constant. We saw that we increased the laser power, which in other words, we also increasing volumetric energy density. We saw that the mechanical property gets better, for example. First of all, for example, comparing these two, ductility is almost similar, but UTS is different. So almost kind of getting tripled. And then changing other process parameters, for example, going from power of 200 going to, for example, this CG case, which is with other process parameters similar to those, but we have a power of 350. So going from 200 to 350, we have, again, look at the ductility, how the strain and fracture the level when we compare to the other case. And in other cases, we change, for example, speed and so on, and effect of the also, for example, build direction as well. For example, we can see here, so build orientation, that's better term to refer to these cases. And we can see that, for example, in our, the kind of device that we have, yes, there is a level of anisotropy, but it's not that much large, the level of anisotropy. They are not exactly identical, but there are some level of anisotropy. And the best cases that we got in terms of the ultimate tensile strength and also ductility as well is with the lowest scanning speed. So the process is slow, and then we let the laser to completely melt all the powders, right? So instead of going fast, and then we might have some kind of lack of fusion at some point, or introduction of the porosity, then in these cases, it's really slow, and then we have kind of this volumetric energy density being completely uniformly distributed over a specific time frame, allowing our scanning direction. And in case of Inconel, we had somehow a similar trend as we saw with stainless steel, so increasing power. So we wanted to see also from there to there. So here we can see that we added 2 steps as well, a power of 150 and another power of 250 as well, because we didn't know that the trend is exactly going like the ductility is going to change as well, or no, is it going to be similar? And from there to 350 as well, what's the trend? Because from there to there, we have a huge gap in ultimate tensile strength. And from 200 to 350, we have a kind of a huge gap in terms of the elongation of break. So we wanted to see, is it exactly a linear trend or not, or what's the case? So that's why we added those 2 intermediate steps for power as well, 150 and 250. And we saw that, yeah, it's kind of similar trend to what we saw there, the same kind of, and we increase power or volumetric energy density. Again, it helps to have the better mechanical property. And the best one that we got over there, it's our case, the optimized version that we can see. So the lowest scanning speed among our chosen ones, so a scanning speed of 1400 millimeters per second, a power of 350 watts, a layer thickness of 30 micrometers, and also a vertical kind of orientation for the sample. So that gave us the best mechanical property for Inconel. We didn't go back to print the same like the kind of the same process parameters using stainless steel, but we are going to do that as well to see if the same set of process parameters that we use to have the best among those, again, don't get me wrong, it's not the best optimized set of process parameters that you can use using LPBF technology. Based on those that we tested, it gives us the optimized set of kind of mechanical property. But we are going to, in the future, we're going to test that as well. That if we use the same set of process parameters, do we also get the optimized mechanical property as well when it comes to stainless steel? So alloy is different. Everything is fixed. Machine is fixed. Process parameters is going to be fixed. The only thing that we are going to change is the material. And we wanted to see that as well. Yeah. And just an example of the different cases that we tested. So regarding the anisotropy, so we can see here, so first of all, what is happening when we do mechanical testing. So this is before static testing, and this is after. And we have a kind of a small portion, small area that we can see that there is a necking, a small necking. Not exactly as we see in conventional kind of materials, but in some cases we can see the necking as well. And as I referred in the previous like the slides, is that we see some level of the anisotropy, but not that big. So for example, if you look at ultimate tensile strength, so the difference is not that big. So maybe less than 10% differences. Of course, in some cases, even 5% differences in different direction is going to be crucial for us, or critical. But we saw that using this machine, that we see that level. Again, it changes if you go from one machine to another machine. It's not fixed. If you use the same set of process parameters and we use another machine based on LBPF technology, I don't think that we are going to get exactly the same mechanical property. Okay? And that's also, that's also just looking at the macrostructure, like the kind of using a scanning electron microscope when we look at the fracture surface over there. And we see that, for example, there are some voids, for example, primary voids, that they were there because of the whole the process that we use, and also secondary voids as well over there. And we also analyzed other kind of like the micro features as well. And was it here or someplace else? I think, yeah, I have it someplace else that we published something like the last year. And besides doing kind of a tensile testing, we also try to measure porosity, which is a main factor when it comes to additive manufacturing, and also another property hardness testing as well. So the level of the porosity, as we can see in different cases. So we can see, for example, in this CG is one of the best cases, and this one is one of the best cases as well. And then we can see the level of the porosity is really low, 0.6 or 0.7. So that's really low, but it's not the minimum that we can achieve. We can also lower that as well. And the hardness, so we did hardness testing to just evaluate. So in this case, we tried, and then we saw that because of a lot of problems, lack of fusion everywhere, the huge amount of porosities, because the powders, because of the low level of the volumetric energy density, didn't melt uniformly, and then we couldn't do any kind of a uniform hardness testing over there. And for Inconel, so we also did a kind of a porosity measurement over here, and we can see that here as well, for example, over there the porosity was 19, and here as well was somehow close to that one as well, the porosity, level of the porosity. And in order to do that, what we did, we followed exactly the same process parameter definition as we did for tensile testing, and we produced a different set of samples, mainly to do hardness testing. Of course, we could also use the tensile sample itself and grab, for example, the gripping area and to do the hardness testing. What we wanted to not kind of having any influence from the kind of other mechanical testing in the other one as well. So we just produced like the kind of dedicated samples to do hardness testing. And we can see that the distribution of the porosity is somehow similar to what we see in stainless steel and in Inconel as well. And we can see that, for example, when it comes to the optimized, which the layer thickness is the smallest, so we have almost the smallest porosity as well. And this case as well. So in this layer thickness of 30 micrometer, we do have also the same size of the layer thickness, but the scanning speed was a different. If I don't want to give wrong information, so I want to go back. So no, we have a kind of a larger kind of a scanning speed, but the layer thickness, power was the same, and also build orientation was the same as this one. As we can see that the level of the porosity was similar, but hardness, look at the hardness. So over here, so we have a kind of a hardness of around 80 something, but over there is close to 95. So hardness was different, mainly because of this process of like the slow, the kind of a scanning speed, having a uniformly kind of fusion between all the powders and so on, that helped to have a better hardness. We also measured her surface roughness, so different aspects. And as I said, this is also a critical parameter. Not necessarily when we do static testing. This is really critical when we do fatigue testing, surface roughness. But we wanted to evaluate that and correlate that with some of the static mechanical properties. And we did the measurement for stainless steel. We did the measurement in a collaboration with Aarhus University, and also in this collaboration, what we are doing currently is that we want to correlate some of the static mechanical property with the surface roughness, but also obtain in the near future some of those properties using some, for example, scratching and so on. So we want to do that as well. And as we see that while we increase the volumetric energy density, for example, RA, the vertical one, so which is in this direction. So RA also kind of decreases when we increase volumetric energy density. And we see somehow that similar trend over here as well. And when it comes to printing in a different orientation, we saw that mainly was a kind of a challenge, because if you printed like in a vertical direction like this, right, then the outer boundary kind of for this is, because when we do the slicing, so you have to imagine that every layer is like a kind of a what do you call a hexagon, right? Like the kind of in a two direction, I have a rectangle, and then I have the thickness along the way. So if I'm printing in a vertical direction, then the boundary of the sample and that single layer, they're going to coincide to each other, right? But if I'm printing angled, right? So this is the line of the boundary. But the layer, I have some excess kind of edge that I have, right? And that kind of contributes to have a larger surface roughness when we print samples in angled kind of orientation. And that also, again, we knew that from the literature, okay? It's not something that we discovered in this research. But we wanted to see what's the level when we change those different process parameters, not only being angled, but also change other process parameters. We wanted to evaluate that. And we saw that as well. So when we change, for example, this 90 is exactly being horizontal, okay, like this. So being completely horizontal, and 0 degrees means we print vertical. And then from there, we measure the angle. So 15 is this, and then we have 30, and then we have 90 degrees. And we saw that the effect of all those, for example, having this 15, the lowest kind of RA among those three cases, and then the next is 30, and then the next one is 90 degrees. And a correlation between these two and the ultimate tensile strength, that we see that, for example, in the case that we had the highest volumetric energy density. So we had the lowest surface roughness and the not the highest, but almost the kind of one of the second highest ultimate tensile strength, right? Only. And that's a kind of a, again, surface roughness is not critical for us when we do static testing. It's critical mainly when we do dynamic test, fatigue testing. And I'm going to discuss that as well in detail. But this is just a kind of a correlation that we saw in our cases. We also measured melt pool geometry. And we did that only for in-canal, just to see what's the size of the melt pool, depth of the melt pool, and also width of the melt pool as well. And in order to do that, some researchers, what they do, for example, if they have, for example, a vertical kind of build orientation, so what they do is that they just cut the sample in this vertical direction and follow, for example, this etching process, and then look at the etch surface and to obtain the melt pool geometries. But if I cut the sample, for example, from here, and that's the top, for example, this is the cutted surface, and that's the top. So that surface, which if I say that's a reference for me to measure the depth of the melt pool, that's not the actual reference, right? Because there is also the top layer that I cut it, and maybe a part of that was changing the subsequent, not the subsequent, but the lower layer melt pool geometry, because we know in this process we do have remelting, right? When I print the current layer, I do also have remelt the lower layer as well. So the best way to measure the melt pool is that you produce a sample, small sample, and this surface over there is the last layer, okay? That should be the last layer that you print. And then that last layer, whatever you see over there, depth, width, whatever you see, that's the actual melt pool geometry for that layer. And that's exactly what we did. We produced small samples, specifically only for melt pool measurements. And again, Ahmed did all those, yeah, and following this etching process and so on, and we saw that. And we wanted to, because this again, all those process parameters affects this as well, the size of the melt pool, depth of the melt pool, and so on. And that affects the overall mechanical property. Yeah, another analysis that we did based on this static testing was using X-ray computed tomography. And with that, we wanted to evaluate the level of the porosity in our sample. As printed sample, no post-processing, nothing, no heat treatment, even no surface polishing and so on. Whatever we see is as printed. And also evaluate that once we do kind of tensile testing in a step manner. For example, do the tensile testing, stop it, measure the porosity level, mainly to build a numerical model for ourselves to evaluate the whole process. And for example, we can see here, this is the sample before doing the tensile testing. And we only look at a kind of a region of interest, middle of the sample. And here we can see, for example, the volumes of the oil. So this, the kind of a purple color mostly, and some places we have a kind of a yellow ones, are like the pores inside the sample. So going from purple, we have the smallest, and then when we go to higher, we have the kind of largest pores. And we can see even as built, we do have porosities, right? Even with the optimized process parameters, we see that. So the porosity is there, and that affects mechanical behavior. Again, this porosity, yes, it has its own contribution in the tensile behavior of the sample, but also main contribution in dynamic fatigue behavior of the sample as well. And what we did, mainly to build a numerical model, was that not only measure it at the beginning, so 0 stage over there, but doing in, like we measure the level of the porosities in different intervals over the same sample. So for example, if this is the initial porosity level, and if you call this nucleated the volume void fraction, so if we call that, so if this one is, if we assume that that's 0, then at different interrupted stage, we can see that that increases, okay? So the same sample, we just stop the test, do XCT, come back again, follow, continue, for example, from 1 to 2, stop the test, do XCT, again come back, and so on. And the reason to do that was, again, to build a numerical model for ourselves, okay, mainly to do that, but also to evaluate what is exactly is happening when we have some initial porosity distribution, and then once we do this testing, what are the kind of this kind of a growing of this porosity is happening? Is it uniform growth of those porosities, or you see a concentration of this growth and also joining of those porosities at a specific location? That's also was the aim, to study that one as well. So what is happening? Because everything that is happening is in there is because of the nature of the produced part, right? Because of those set of process parameters that we use. We wanted to evaluate that one as well. And that was the aim. And so all this that you see here, we're going to soon have a kind of a publication out, hopefully. And as I said, for the stainless steel, so this is just a wrap-up of all the static testing like this, like the tensile testing that we did. So here we can see these are the results from our own tensile testing using a laser spot size of 50 micrometers. So the beam diameter was 50 micrometers. And we see that the comparison with others that they used not exactly the same spot size, but in the range of less than 100 micrometers of spot size. And we see some kind of, in some cases, for example, the elongation in our cases works better than the others, but not the best ultimate tensile strength that we could get. Again, all those, not only the laser spot size was different, but also set of process parameters. So it's not easy to find the same, like the exact process parameters that we used here and in the literature. Of course, a different way was that to look at some of the literature and grab a set of process parameters that are identical to those, and then we could compare one to one. But we wanted to define some set of process parameters that we also not only target a kind of a product, like the kind of a good productivity rate, but also evaluate our machine as well. So that was our aim. And we changed the laser spot size to 100 micrometers, so keeping everything the same as in this case, but only changing laser spot size. So the same, if we talk about, for example, this case, so we had the same power over there as well, the same scanning speed, the same scanning strategy, the same layer thickness, and so on and so forth. The only thing that was changed was laser scanning, like the laser spot size. So that was the only difference. And as we can see, for example, so what are the differences that you see? So here, the distribution of, like for example, the elongation and also ultimate tensile strength were mostly kind of close, but over there, they're kind of a dispersed kind of a distribution. So what the main reason is again, the same parameter that we see over there. So the laser transfers the same amount of energy over a wider region in this case, right? So instead of like having the distribution of this amount of energy over a small region, now we have it over a larger region. And that's why we have some differences, for example. So over there, so we can see that most of the ultimate tensile strength we had kind of more than 500, but here we only had one case that it was more than 500. So that's the only reason that we can see that distribution of this energy density over a wider region, rather narrowing and concentrating over a smaller region in this case, right? And that changing the laser spot size, you don't see that much in the literature as well. So for example, most of the, if we compare the number of literatures that we could find for stainless steel for a smaller spot size, look at the number, and how many we could find for larger spot size, more than 100 micrometers. Most of the machines in LPBF, based on LPBF technology, they use laser spot size more than 100 micrometers. Typically 100, 150, 200, something like this. And that was a little bit hard for us, but we wanted to evaluate that one as well. And that's also a capacity of our metal 3D printer, that we can use these two different laser spot sizes. And the main reason, as I said, is because of this, and it was published at the beginning of this year, so we can, if you want, you can just have a look at that one for further details. And we did the same comparison for Inconel 625 as well, but in this case we only used spot size of 100 micrometers. So because we already had some ideas what is happening there when you use 50 or 100 micrometers of spot size, and we didn't want to evaluate the same thing again. So here is just laser spot size of 100, and we see some kind of a comparison over there. And what we see is that, again, the same scenario, that what even the optimized batch that we had, it didn't deliver the best kind of property when we compare to literature. Again, the main reason was that those set of parameters, process parameters that we used, they weren't the best process parameters that we could use. Right? We could use a different set of parameters, deliver the same volumetric energy density, and that was the main reason. And we want to evaluate further, and our aim is to go there. Okay, not only increase ultimate tensile strength, but also kind of having a better ductility as well. So what kind of set of parameters that we can use, that we can shift this optimized version to have a new optimized set of process parameters that we can go over there. Okay, and that's going to be, it's not going to be easy, but it's doable, that we know. And in order to do that, what we want to do, of course, this is also kind of a future work, is that we want to use also kind of a optimization problem. I'm not going to say machine learning, because you hear machine learning a lot everywhere, but the optimization process, I'm going to just call it. Optimization process that we can use, a better optimization process that we have here. So in a limited number of experiments, we can go there using the same machine, different set of process parameters for the same alloy over here. And it was a collaboration. Of course, this one is not published yet. It's under kind of a review process and so on. And it was a collaboration with Ahmed and our colleague from Osaka University in Japan. So we try also to do not only inner collaboration in our university or only Denmark, but also do international collaboration, and mainly to use the kind of resources. Again, I'm not a material scientist, so I try, for example, our colleague from Osaka University helps us in order to evaluate kind of microstructure, for example, using EBST, for example, and that's the capacity that we don't have in our campus, and then we can use our colleague in that case. Yeah, numerical modeling, the second part of our research after doing the static testing, and this was in parallel to what we did in our experimentation based on tensile testing. It was in parallel, and our idea was to create a numerical model. It was based on continuum mechanics, so we didn't use kind of discrete methods. So we used the continuum mechanics in order to evaluate the parts and so on, And we use Abacus as a software, and we only did for Inconel, mainly to evaluate some of the field variables such as temperature distribution, stress distribution, residual stress, especially distribution, and so on, because we know that when it comes to LPBF process, residual stress is something that it cannot escape from, something that we see. Yep. And what we see here, for example, residual stress distribution, just as an example over here, and we can see that, for example, we compare this with a kind of a literature, and we can see that our model kind of, with a good accuracy, can predict the residual stress when we model this LPBF process. And we had this work was published this year again. And the last part, which is our recent work as well, it still is ongoing, is dynamic testing or fatigue testing. And what we did in this fatigue testing process was we focused on stainless steel 316L and also a scam alloy in collaboration with our colleague from University of Kent in UK. And we did only in our lab, we did only axial fatigue testing, and we focused on the low cycle fatigue to run short time test only, and we used the optimized set of process parameters that we obtained from static testing just to evaluate that what is happening in dynamic testing as well. And we used flat samples to capture temperature distribution because we wanted to evaluate temperature as a way to evaluate the fatigue life of the sample, not only relying on the kind of conventional evaluation of the fatigue life, but also using a entropy-based process and round samples for fatigue life estimation. And as I said, surface roughness when it comes to fatigue testing is one of the most critical factors. And in order to evaluate the surface roughness, we can use, for example, again, the same technique as XCT. Again, yes, it is really expensive to use X-ray computed tomography, but it helps us a lot, not only surface roughness, but the porosity as well. And thousands of slices that we can have, and then we can have, for example, for one slice, if you look at one slice, in some cases that, for example, we can see some kind of a surface kind of defect, and then some inner porosity is close to that surface defect. And once you do this dynamic testing, like cycle by cycle, you might see that this inner surface kind of rough, like the void, joins the surface defect, and then they become like a kind of a surface crack. And we saw that even in our experimentation, not yet that we say that this is the reason, but this is the most probable reason that we saw that, for example, multi-site cracking in our samples and failure. So, for example, if we look at this stainless steel, for example, look at here. So we had multi-site damages happening. Of course, one of those becomes the largest crack, and then it becomes the crack in the sample as well, and then we had the crack propagation over there, but we saw that we had multiple sites, and that's the reason. A combination of the surface roughness together with the internal voids becoming the kind of multiple surface cracks, and then they start to grow, and one of them becomes a dominant one, and then you have the fracture from that surface. And when it comes to round samples as well, for example, necking happened. And in this fatigue testing, we saw the necking. So here is the stainless steel. Over there is the scam alloy that we saw this necking is happening. But when we look at the surface, kind of the fracture surface, so we saw that the same kind of the fatigue surface, not the fracture, I'm sorry. The fatigue surface, the same kind of a fatigue surface as you see in kind of conventional materials as well. So that we saw. Not in this stainless steel, it was kind of different than what we saw in the conventional stainless steel, but in this case of a scam alloy, which was printed using a different printer outside our center, so we saw kind of a similar. And the reason was that here we use a fixed set of process parameters. Over there, in that kind of our colleague at Aalto University, they use kind of a dynamic set of process parameters. So they changed the process parameters allowing the build as well. So that was one of the reasons. Yeah, And this is just initial fatigue testing results. So bending test was done by our colleague, and we did axial fully reverse fatigue test. And one of the things that we see even in the literature as well, but we saw as well here in our fatigue testing, that scattering. So the same sample with the same set of process parameters. So material is the same, loading is the same, the same set of testing as well. When we test one sample, we saw that, for example, the fatigue life was 100,000 cycles. And when we test the next sample, it became 350,000 cycles. Nothing changed. The same, and scattering. That's why I'm saying that reproducibility, repeatability is a challenge when it comes even to this LPBF technology. And that we want to evaluate further using XCTs and so on to connect that with fatigue testing. Yeah, and then just the last slide, Ahmed. Yeah? And what we saw that when it comes to fatigue testing, for example, so as I said, we had, based on our set of different process parameters, we had optimized process parameters based on those, not the best ones that we could use, but some of those that we could use in our cases. But those not necessarily are the best optimized process parameters for fatigue testing. I didn't put any results here yet because they are not published. So maybe later I can share those information with you. Not here because this is also live streaming. But we saw that. And internal defects can be controlled if we changed process parameters dynamically during the build process. So that we can control. And again, when it comes to fatigue testing, that's really critical. We should be able to do that. And surface characterization is really, really important. There are different ways that you can kind of correlate this surface roughness and also estimate the fatigue life as well. And our colleague from University of Kent, we are going to do that kind of estimation for our samples as well. So do a kind of a prediction by evaluating the XCT and also the surface roughness, and do the fatigue testing over here and compare these two together. The prediction and actual fatigue testing. And we want to see how effective is this process that they already published with a different machine, different alloy, with our machine and our alloy, to see how effective it should be, because they have promising results, but we want to evaluate that one as well in our case. And what we want to do is that we already are doing it as well, is to use thermal camera to get the temperature distribution of the sample. Not the round samples again, because we had difficulties when it comes to round samples because of the cross section that we want to, not the cross section, but the area that we want to look at the temperature distribution. But so we want to use, typically we use flat samples in that cases. And we see that, for example, when you do fatigue testing, the temperature goes from the room temperature, which was around 25, in some cases to 70 degrees, okay, in the fatigue testing. Of course, there are different reasons, internal friction and sliding and so on, everything. And we saw that. We want to use entropy-based like technique to estimate predict the kind of have an estimation of the fatigue life and correlate with what we see here with actual experimentation. And a camera to do the crack growth analysis. That's also something that we are currently doing, but we want to further study when we change again those process parameters and see what is happening over there. First, the typical step is, for example, to obtain Paris Law's constants, for example, for stainless steel, Inconel, aluminum as well. So we want to do that under different conditions. When we change, for example, frequency, we know that they're not going to have the same constants. It's going to be changed, and then we want to evaluate that one as well in further studies. Yeah. If there is any question, I would be happy to answer to the best of my knowledge. Yep.
I understand that you normally utilize micron-size powders, right?
Yeah.
And what would be happening, if you use maybe smaller ones? Would it be possible that, use them and get much better, maybe surface properties or less porosity? Like, have you done such experimentation before? Like nano-sized powders compared to micro-sized powders?
Definitely so when I talk about the different process parameters, so maybe we can go. When I talked about different process parameters, so here, and one of the process parameters is this powder size distribution. So morphology of the powder, even the chemical composition of the powder. So if we have our layers, for example, here, just a schematic, so the larger powder, for example, so I said that in some cases we had laser like the spot size of 50 micrometers. And if I go back, if I go further, so to here, so we can see that the manufacturer says that some powders might have a kind of a size of close to 50 as well, micrometer, right? And it means that the spot diameter is exactly the same as the size of the powder, and it might not have kind of complete melting of the powder. So if the size of the powder is smaller than that, for example, instead of saying an average of 30 micrometers, we have an average of 10 micrometers, definitely the bounding would be better, fusion would be better. But we didn't try that because if you go from this size distribution to a smaller size distribution, cost will be much more. But that's also a possibility. Yeah, that's really interesting to see. This is just my kind of understanding this is going to happen. But what degree, for example, how much it helps, that I don't know. But that's possible that we can do. The only thing is that we didn't want to change that process parameter. Where is it? We didn't want to change that one. We didn't want to change a lot of process parameters. We just tried to focus on 4-5 different process parameters and focus only on that. Powder itself wasn't among those, but that's an interesting topic to evaluate. Yeah.
Başka sorusu olan var mı? Okay, so I would like to thank you, Mohammed, for this nice presentation. Today, actually, I insisted Mohammed to have this technological conference for us. I would like to provide, say thank you for these 2 years that I had in Denmark, in Sonneborg, because Mohammed, as a lab responsible, as a supervisor of me for 2 years, he provided us in the laboratory, he provided us an excellent conditions, like both physical conditions and also mental conditions. I cannot describe the how happy was I am in there for 2 years. This was because of because of my supervisor, Mohammed. And also, again, I would like to thank you for today, for the nice presentation. Also, some parts I didn't see of this presentation, especially dynamic parts and surface roughness part and so on. So it was also, for the last 2 years, I learned a lot, and now I'm continuing to learn with you again. So. Again, thank you for the presentation.
Yeah, thank you. Yeah, thank you again, Ahmed, for the invitation. It was kind of really nice to be here. And when you say supervisor, I feel I'm old. I'm not. We're colleagues, so yeah. And then, as I said, So most of the kind of the parts that I presented here, so it was a kind of a joint work with Ahmed. So except the fatigue testing that we did recently, but the static, whatever we did together. Mostly when I say together, mainly Ahmed did. I was just trying to facilitate all the process. Yeah.
The idea is coming from you. So.
Yeah. Thank you very much. And it was a pleasure being here, and I hope that I have some kind of nice collaboration in the future with some of you. You are more than welcome to visit us. And I didn't show other facilities that we had in our campus. So just also want to thank the labs that you see, that are those facilities. So they came with the kind of supports with different kind of funders and companies that we do collaboration with them. In our campus, not only we do this kind of mechanical testing, so when we talk about microstructure, we do have a lot of facilities for material characterization. So we do have scanning electron microscope, ion helium, a kind of microscopy. We do have AFM, for example. We do have XRD devices as well. So everything that someone with a mechanical background interested into evaluating material characterization of metallic or non-metallic parts are there. So I'm lucky. Ahmed was also lucky that we had everything there. And if you have any kind of ideas that you think that you don't have the capacity here, we would be happy to help you with that one. Yeah? Yes? Thank you again.
Thank you.
Yeah?